So we're now on to the final topic this semester that we'll talk about. And this has to do with Bayesian inference and Bayesian statistics as it relates to indirect negative evidence. That's what INE stands for in these slides. And the poverty of the stimulus. That's what POS stands for in these slides. We're going to be trying to tie all of these together. It's going to take us a while to get there. So we're going to start out this unit with some background about Bayes' theorem and how it applies to different kinds of learning or inference situations. We're going to progress into considering some relatively simple linguistic examples of Bayesian reasoning. We're going to take a short detour to look at a sort of fallacy or a cognitive illusion that arises when you start thinking about things in Bayesian terms. That's not going to involve language at all. So we're going to go sort of far afield. And then finally, we'll come back and look at how this Bayesian framework is applied to the anaphoric 1 situation according to Regier and Gall, as well as some problems in there. And then the last section of this unit, I'm going to see how long it takes to lecture through the rest of this. But if I have time, I'm also going to go through some more general demonstrations of what happens when you try to apply Bayesian ideas to really complex and detailed linguistic data and some of the problems that arise. So yeah, let's start off. Remember, we're going to take a step back and be looking at non-linguistic things a little bit in this unit before we come back to applying Bayes' theorem to language. Okay, so here's what happened with that Lids paper and the responses to it. So they proposed a particular kind of poverty of the stimulus argument. They support it with some corpus studies about inaccessibility and with an experiment showing that the facts are nonetheless acquired. And then other researchers were trying to poke various holes in that indispensability argument. So maybe there's another way you could have gotten these experimental results, even if there were no innate universal grammar governing the X-bar architecture or something like that. And we're going to focus in again on this Regier and Gall idea that maybe children have the generalization, but that they actually have learned it from consideration of what they didn't hear in the data. And this is again referred to as indirect negative evidence. And so here's my sort of simple paraphrase of what indirect negative evidence is about. The idea here is something like this. Well, my grammar predicts lots of things should be grammatical, but I only ever hear some of them, and other of the grammatical things I predict don't ever seem to show up in my environment. Therefore, maybe I should try to select a more restrictive grammar. That's the basic idea behind indirect negative evidence, right? You can have grammars that predict lots of things and grammars that predict fewer things. And in a world where you don't hear everything that the bigger grammar predicts, you might want to just prefer the more restrictive grammar because it provides a better match to your experiences. There's many ways that you can capture this kind of mathematical idea in different kinds of learning frameworks, but Regier and Gall think that it's particularly natural in the general framework of Bayesian inference. And Bayesian inference is one of the central paradigms in modern cognitive science. All empiricist theories, more or less, nowadays rely at some level on Bayesian inference, on some process of inference that could be called Bayesian. So let's talk more generally about what Bayes' theorem is and what it says and what it means for a learning theory to be Bayesian. Oops. So this good-looking gentleman over here is the Reverend Thomas Bayes. He was an English pastor who lived in the 18th century and also a mathematician because people did things like that in those days. Right? And so what Bayes created is essentially a description of normatively optimal method for updating your beliefs in the face of evidence. What do I mean by that? Well, he means this as a theory of how you ought to reason. Right? So this is meant to be a prescriptive theory. If you want to make the most rational possible updates to your beliefs based on the evidence around you, this is mathematically how you ought to optimize that process. Right? So it's a theory about how you should behave or the best way of inferring things. And the basic idea here, in conceptual terms, is that to know how likely an explanation for some set of observed facts is, you need to know two things. How likely is that explanation independently of the things you've observed? And this is referred to as the prior probability. And how likely would you be to observe exactly the things that you have if the explanation were true? And you need to trade off these things against other explanations, right? So for each possible explanation, you're going to need to know these two things, right? And these are the main components of Bayes' theorem. So here's what the theorem says in slightly less abstract terms, although this is still a pretty abstract statement of it. And what it says here, it's about conditional probabilities. What does that mean? Well, this pipe notation means that we're looking at the probability of this thing if it's the case that this thing is true. So the probability of this thing given this thing or conditioned on this thing. Now here we're using H to stand for a hypothesis, some kind of an explanation, and D to stand in for some kind of data, things that we've gathered in the world. And the idea here is that we eventually want to know for all the different possible hypotheses that we might come to, what's the probability of each hypothesis given the data that we've seen? That's the problem we're trying to solve. Right? What's the most likely hypothesis, the most likely explanation for the things that we've seen in the world around us, the data? What Bayes says is that this probability is proportional to, that's what this little symbol means, first of all, the probability of having observed exactly what we have if the hypothesis were true. Right? So a good hypothesis will predict things that look like the data we've observed. And this particular component of the equation here is referred to as the likelihood of the data. It's the probability of the data given some hypothesis. And of course, we can compare various hypotheses and see which one makes the things that we've observed most likely, and all else being equal, that one will be preferred, right? So we want to maximize the likelihood of the data, and that's one of the criteria on which we select hypotheses. But also, and this is the sort of novel or interesting part about Bayes' theorem, it's not just about what we've observed in the world around us. We also should incorporate everything that we already knew about the hypothesis space. And he refers to this independent probability of the hypothesis, independently of what we've observed about the world. How likely is this hypothesis to be right? That's referred to as the prior probability of the hypothesis. So what this says is that this is also, I didn't write this down here, but the thing that we're trying to solve for, the probability of different hypotheses given the data, that's what we eventually want to learn. This is referred to as the posterior probability. That's what we're trying to get out of our inferences. And Bayes' theorem says that the posterior probability is proportional to both the likelihood of the data given that hypothesis and the prior on the hypothesis. So you're going to combine these two things in some way for all sorts of different hypotheses, and then the one that optimizes this product is going to be the one with the highest posterior probability. So this is how we're going to update our beliefs about the world. We're going to start with the all-purpose statistical demonstration here, which always involves flipping a coin, because this is a very simple binary Poisson process. It's random, and we all have a good intuitive understanding of how flipping a coin works. And so let me show you first how likelihood works without any priors, and we'll see why it's a problem to do only data-driven learning with your likelihoods and not have priors in the theory. Here's what happens. So hypothesis one here is that the coin we have is a normal coin with a head side and a tail side. Hypothesis two is that it's a trick coin and it has only heads on both sides. Our data here is going to be a certain number of coin flips that all come up heads in a row. And so we're going to ask, given this many coin flips with this many results that are the same all in a row, what's the relative probability that it's a normal coin with heads and tails versus being a trick coin that only has head sides? Right? Well, here's the likelihood without any priors. So what does this say? The red line here is hypothesis 2, that this is a trick coin with only heads on it. And the blue line is hypothesis 1, that this is a normal coin with both a heads and a tails side. This vertical axis is the posterior probability. It's really the likelihood, right? And this is without any priors on these two hypotheses. And here's values for different numbers of coin flips. So what does this say? If you flip the coin exactly once and it comes up heads exactly once, according to this, there's a 2/3 probability that it's a trick coin that has only heads, and a 1/3 probability that it's a fair coin with heads and tails. Right? So that's already looking pretty weird. That's probably not what we'd conclude in real life, but this is how the likelihood function works anyway. And then as you get more coin flips that are all coming up heads, the probability that it's a fake coin with two head sides gets higher and higher and higher and approaches 1 without ever quite reaching it. Similarly, the probability that this is a normal coin with a head side and a tails side declines and declines and declines and eventually approximates 0 without ever quite reaching it. Right? This is telling you as you get more and more coin flips coming in that are heads and heads and heads and heads, you should believe even more strongly that this is a trick coin and not a fair one. So after, say, 3 heads in a row, you should be 90% certain, roughly, that this is a trick coin, and only 10%, well, not certain, but assign a 10% probability to the idea that it's a fair coin. Right? So this is how the likelihood function works, and this is because if it were a fair coin, for sure, you could observe a heads, and you could even observe multiple heads in a row, but that's going to be very unlikely if it's a fair coin. As you get more and more heads, it's going to be less and less likely that you would ever observe that from a fair coin. Whereas with a fake coin, it's always going to predict that you get lots and lots and lots and lots of heads in a row. So the relative likelihoods of those two hypotheses are in this relationship. Right? So there's some problems here. What's the main problem here? Well, in real life, if I give you a coin and we flip it to decide something and it comes out heads, do you think there's a 2/3 probability that that coin is a trick coin and that I tricked you? Probably not. You're probably almost 100% sure that it's a fair coin, right? There's no reason to think that it's a trick coin or a fake coin. What's the reason for that? Well, according to Bayesianism, one reason why we think like that is because we have strong priors on these kinds of hypotheses. Right? So before any coin flipping happens, we don't start with the idea that half of the coins we see are fair coins and half of them are trick coins. We have a whole lifetime of knowledge and experience behind us. And, at least if you're like me, the number of trick coins you've ever seen in your life is extraordinarily small, right? And you've never really been tricked by a fake coin before. So you just assume when people are flipping coins, they're much, much, much more likely to be normal coins than they are to be trick coins, right? This is what priors are for. So here's what the function looks like with some pretty strong priors. And these might not even be as strong as the priors in real life, but they're at least just illustrating the point here. Now we're going to look at the posterior probability here, incorporating both the likelihood of observing this many heads in a row and with strong priors. These priors are going to be 99% it's a fair coin and 1% it's a fixed coin. So what does that mean? It means that we're going to start out, before we've ever flipped any coins, expecting with 99% certainty that any given coin is a normal coin with both a heads and a tails side, right? So here we start at 99% in favor of a fair coin, we get one coin flip, and you can barely see it in this graph, and maybe it decreases our certainty a little tiny bit from 99%, but not that much, right? The priors are doing something here. They're preventing you from jumping to wild conclusions based on a little bit of data. Now, we get a second heads in a row, and it budges again a little bit. Maybe we're now down to, say, 97% certainty that this is a fair coin. But because we started with a really strong expectation that almost all coins have a head side and a tail side, we're not completely throwing that away when the coin starts coming up heads and heads and heads. Now, as we get more and more and more heads piling up, eventually we start to consider, I came into this situation thinking that it's almost certain that this was a normal coin, but now I'm kind of beginning to wonder, because we've just flipped, let's say, 5 heads in a row. That seems pretty unlikely if this were a fair coin, and more likely if it's a fixed coin, right, with 2 head sides. So now at this point, maybe my certainty about the fairness of the coin is going to be down to maybe something like 70%, and I'll assign something like 30% probability to the idea that this could actually be a trick coin. And then depending on how strong you want to make the priors, at some point we get this crossover where we've now seen so much evidence that's inconsistent or unlikely under the hypothesis that this is a normal coin that we actually cross over to thinking that there's more than half a chance that this is actually a trick coin, right? So in this particular simulation, this happens right around 7 heads in a row. And of course, you can quibble with that, whether that's the right or the wrong number, but you can change that around just by changing the actual quantitative values of the priors in whatever ways seem most convenient to you. The point here is just what this simulation says is that we start out with very strong beliefs about coins, and in order for those prior beliefs about coins to be overcome, it takes a large amount of extraordinary evidence, right? So if a coin's coming up 10 heads in a row, at this point, now we become reasonably certain that this is not a normal coin. So we're about 90% sure that there's something wrong with this coin. It either has 2 heads, or it's weighted unevenly, or somebody's playing a trick on us, or whatever, right? So you can still learn from data given strong priors. It just takes a lot more data, and this seems to be normatively optimal with regard to how we ought to reason about the world. The claim in cognitive science is that it also is descriptively correct that people actually do this. And so I've picked the coin flip example here to try to show an intuitive case where it really does seem to be true that we start out with strong priors, and when we infer things about the coin, we incorporate both those strong priors and the data that we're looking at, or specifically the likelihood of that data. So pretty much everybody, at least everybody who works in math and statistics, agrees that Bayesian reasoning is the best way to update beliefs. That is the best way to learn, right? It is mathematically optimal for learning. Some people also think Bayesian reasoning is the actual way that implicit human inference and learning work, right? If that's right, then it should be possible to describe cognition in Bayesian terms. And this is exactly what some large branch of the cognitive sciences have been doing for the last 20 or 30 years, trying to show that the way people actually do cognition conforms to Bayes' theorem and is Bayesian in that broad sense. That said, it's still worth distinguishing between prescriptive Bayes, this is the best way to do inference, just about everybody agrees with that, versus descriptive Bayes. People use Bayesian inference in their implicit knowledge and cognition. That's more controversial. Right? So here's a simple example of how you could apply this to one kind of linguistic problem. We're going to go through this, then we'll take a short detour to look at actually disease diagnostics, but to illustrate another point about Bayesianism, and then eventually we'll come back to the anaphoric 1 problem. So here's a simple linguistic example here. Consider two English words that have the same string of phonemes in them, pen and pen. So this is, I'm going to refer to this one as pen 1, it's a writing implement. And I'm going to refer to this one as pen 2. It's an enclosure where you keep farm animals, right? Specifically, I think probably pigs are the most common animals I've heard of being in a pen, although I've also never lived on a farm. So here's two pens, pen 1 and pen 2. And we're going to try to solve the problem of when an English speaker hears a sentence with the string of phones, pen in it, how do they decide which one of these lexical entries is the one that's being referred to? Right? And so as a start here, we're going to need a prior probability on pen 1 versus pen 2. Right? What would that correspond to in language? Well, it would correspond to the idea that any given string of sounds, pen, is this likely to refer to one of these things, and this likely to refer to one of these things. In other words, it's going to be the relative frequency of these two nouns. So how often have we heard the string of sounds pen with this meaning? How often have we heard the string of sounds pen with this meaning? This is actually pretty difficult to do in practice with existing corpora. Because in a corpus, usually this difference between the two is not going to be encoded in a way that you could read with a computer script. So you're basically going to have to go through the corpus by hand, find every instance of pen, and decide which one you think it refers to. That would take hundreds or thousands of hours if it's a big corpus, and so I'm not going to do this. Right? But that said, I picked this case because I think there's very clear intuitions here about which one of these is more frequent in the day-to-day life of an average American college student or college professor, right? It's pretty clear what the relative frequency is going to be like here. So I guess I'll give you a second and let you guess, but I think it's pretty clear. So I'm assuming that in the lives of people who are basically not farmers, right? Average American English speaker, or even average American English college student or college professor or something like that, we're going to hear this kind of pen a lot. And we're going to hear this kind of pen not anywhere near as often. That seems obvious to me. Here's a sort of rough check on that. This is informal, but it, it'll get us a ballpark figure. If you search on Google for the exact phrase ballpoint pen, which is unambiguously this kind, you get 7.5 million hits for that. And if you search for the exact phrase pig pen, which is 99.9% certain to be this one, I guess it could be a writing pen that has pigs on it, but it's more likely to be this. That one gets only about 1/7 as many hits. So it's something like in the neighborhood of 7 to 1 frequency, higher for this kind of a pen than this kind of a pen. So pen 1 has a higher prior probability than pen 2. That suggests what a useful default strategy should be for inferring which word is being used in neutral syntactic and semantic frames, right? So these are frames that don't particularly bias you one way or the other, right? There's nothing about farms or writing implements in these sentences, and so there's no real meaningful reason to pick one over the other, but there's a default strategy here, which is that any given instance of if we're reading these three letters or if we're hearing these three phonemes, is just 7 times as likely to be a writing implement as it is to be an animal enclosure, right? So I need a pen. What are you going to infer about that? Probably a writing implement, even though there's nothing about needing that biases this one way or another. There's a pen over there, right? Obviously, that could be either pen 1 or pen 2, but if you hear that out of the blue, you're probably going to think pen 1, and so on and so forth. So this is the idea that priors in terms of word recognition are going to be basically proportional to the frequency or the commonness of words, right? Which can be very hard to measure sometimes, but we have no doubt that it is a real property that can, in principle, be measured. How about this one now? I put the animals in a pen. Now, all of a sudden, I mean, technically it's possible, again, for either one of the meanings to be at issue here, but I think we now have a pretty strong intuition that the pen we're talking about here is pen 2 and not pen 1. And of course, we're going to want a theory of how this works. How do we reverse our preferences here? Now, in intuitive terms, it's because the meaning of the sentence strongly favors the animal enclosure meaning and is less favorable to the writing implement meaning. It would be pretty hard to put animals into a writing implement unless they were very, very small animals, whereas the other kind of pen would be a natural thing to put animals into. So in sort of, broad terms, we can say, well, why does our preference switch here? Why does our inference change here? Well, because of the meaning of the sentence. Bayesian frameworks allow us a way to incorporate or to describe this process, incorporating a more general form of logical inference. So how is this going to work here? I put the animals in a pen. What does Bayes' theorem say? It says the posterior is what we're trying to discover here. What we're trying to figure is how likely is it that the word we've heard here is pen 1 versus pen 2. This is what we're trying to discover. This is the inference that we're trying to make. And this is going to be the posterior probability of the hypothesis it's pen 1, right, in this context, versus the posterior probability of it's pen 2 in this context. These words are the hypotheses we're testing. Right? And so the posterior is what we're trying to discover. Bayes' theory says that this is proportional to the likelihood. Well, how likely are we to hear this sentence if it were word X that were at issue? Combining the likelihood and the prior, how likely is word X in general, these two, the product of them should be proportional to the posterior probability. So how does this work in its details? Well, the idea here is we start with strong priors, and the priors on pen 1 are high, and the priors on pen 2 are low. That's because of their commonness of occurrence, their prior probabilities, and that explains the sort of default interpretations with, I saw a pen over there. That's why we default to pen 1, because there's not much evidence either way from the likelihood. So we're just reverting to our prior probabilities. And normally when we hear the string of sounds pen, it's referring to pen 1 and not to pen 2. So that's the sort of default case. In this special case with I put the animals in a pen, now all of a sudden we have some new evidence and we need to update our beliefs that were based on our priors. So our prior beliefs were any instance of pen is likely to be pen 1 and not as likely to be pen 2. But how likely this sentence would be, given the hypothesis pen 1, is very, very, very low. Right? So if we were talking about a writing implement here, that's hypothesis 1, then it's very unlikely people would be saying this thing about the writing implement. Whereas if we were talking about an animal enclosure here, so given hypothesis 2, pen 2, it's much more likely that people would be talking about pen 2 in this way. So this is the likelihood, the relative likelihood of these two hypotheses. And if we multiply these out, we're going to get a fairly low posterior probability for the hypothesis they mean pen 1, and a higher, I'm saying low times high equals moderate or something like that, a higher posterior probability for the hypothesis they're talking about pen 2. So I can flesh this out with some actual numbers just to show how it works. These numbers are completely made up, but they're just trying to illustrate a general point here. So in general, what's the prior on pen 1 versus pen 2? Let's say for the sake of illustration that it's 90% pen 1 and 10% pen 2. How likely are each of these, how likely would this sentence be? I put the animals in the pen. With pen 1, extremely unlikely. With pen 2, much more likely. So here I've made this much stronger than the priors because I think that's right. it's something like I've put 99 to 1 here. It might actually be much higher than that. But this is just illustrating the point. Let's say there's a 99% chance, given that sentence, that we're, a 99% chance of hearing a sentence like that if it's Pen 2, and only a 1% chance of hearing a sentence about animals if it's Pen 1. Now we have a prior and a likelihood. We multiply these out and we get these units that are not quite probabilities, they're relative probabilities. So we get 90 units for Pen 1 and 990 units for Pen 2. And now we can just change these to proportions or percentages if we want to, but you can already see the results here. So how likely is this to be Pen 2 as opposed to Pen 1? It's 11 times more likely to be Pen 2 than it is to be Pen 1. And this is how the framework generally works. These exact numbers are probably not quite right, but that's not really the point. The point is just that you can get this to work out, and that maybe for some linguistic processes, like resolving lexical ambiguities, which is what we're doing here, Bayesianism might be a good way of thinking about those cognitive processes where we're incorporating prior information about which words are more likely than other words in general, with information about how likely we would be to see certain kinds of sentences if we were talking about one or the other word. And when you combine these two sources of information, you can get a bunch of facts to work out about neutral semantic contexts on the one hand, and then the one we've been looking at here is a distinctly not neutral semantic context. It's one that very strongly favors one of the meanings. And Bayesianism gives us a framework for integrating these two kinds of information and tries to reflect the kinds of inferences that we might make about linguistic items or cognitive processes in these kinds of inferential situations. Okay, so I'm going to take a quick break here, and then we're going to zoom back out of language for a moment and talk about a really important conceptual aspect of Bayesianism that ends up being somewhat important for cognitive science, but actually ends up being really important for just the way we think about the world and reason practically in the world around us every day. This example involves diagnosing diseases, which has unfortunately become really relevant to our day-to-day lives, but it's more generally getting at some facts about inference and what Bayesianism has to tell us about it in general. And we'll come back for that in the next part of the lecture.